just finished up cleaning up what they're calling the main board assembly, and this is actually the board that all of the power output transistors connect together. And I just got done replacing all these capacitors, these old ones here, and they tested actually pretty good. There was one of them that was bad. All the rest of them tested really good, but you know, you're this deep into it, don't mess around. An interesting thing I found is the schematic calls for these to be 25 volt capacitors, but they're only 16 volt. I ended up putting some Nichicon KT series 105 degree and rated at 35 volts because that's what I had. I didn't have any 25s. I did have some 16s, but I thought the 35s would be a little better for durability. And as you can see, these were radial lead instead of axial lead. It's really hard to get axial leaded capacitors. They're more expensive. You have less choice in the types. So this was kind of my solution. I did like a wraparound type thing with them and then put a little bit of silicone on them or silicone stuff, the non-acidic type. And that should hold them. So those should last a really long time. I checked all of the resistors. A couple interesting things I'm noticing on this amp. Number one, these pots are your bias adjustment pots, and I'll show you what they adjust here in a minute. It's very, very interesting and innovative the way they did this. But there's no way to get to these stupid things. This board is flipped down this way, and you can see over here all you have is these slots. I'm hoping that one of these slots here in the chassis lines up with this, and you're supposed to reach in through there and kind of grab the knurling on these pots to adjust them. I don't really know. I don't know how you would adjust it any other way because it has to be all assembled to be able to power it up. So that doesn't look very easy to deal with. All the resistors tested good. An interesting thing, this circuit of this amplifier is loaded with really interesting things that you don't often see in other big power amps. This is one of them. See these four big things here? These are diodes, but they're not just normal diodes. They are actually high-powered Schottky diodes. So what's their purpose? Let's take a look at the schematic. So the first thing you'll notice in this schematic is that the transistors, the outputs, here they are. There's 3 on the push side and 3 on the pull side. These are your outputs, but they're in series. Much like what we saw on some of our projects we did with the Carver amplifiers, the ones that were like a Class G or Class H with the stepped power rails and so forth. Well, this doesn't really have stepped power rails, but it does use these as like a voltage divider. So if you look, there's a 75 volts at the top, then a 50 volts at this, 25 volts here. So each one is split up in 25 volt sections. But the bigger thing is every transistor amplifier, these big amplifiers with the outputs like this, you'll always see a resistor of a very low value. See that? This one's 0.39 ohms on the emitters. And these are called emitter degeneration resistors is their proper name, but I've always learned, when I learned this from the old timers in the 70s, they always just called these current limiting resistors. Really the purpose of these is a couple things. It does limit the current somewhat. If these transistors overload, these will absorb that overload, and they'll either absorb it and dissipate it as heat, or they'll just burn open and hopefully protect the transistors, which doesn't always happen. As we saw from this last test, this whole side of transistors went bad, but yet these resistors read spot on. The other thing they do, though, more importantly, is whenever you have transistors like this in complementary pairs, and even when you put them in parallel, you're never going to have, even so-called matched transistors are not perfect. And because of the differences in the transistors, one will always tend to dissipate or more energy or draw more current than the others, depending upon things like the gain of the individual transistor and things like that. So these degeneration resistors actually help absorb the differences between the transistors. So they're very important. The problem is when you add this resistor in here, you're adding a component between the active device here, which is this transistor, and the load, which would be your speaker. And anytime you do that, that will affect the damping factor. It will affect the sound somewhat. So if you want a really solid sounding bass and so forth, you want to keep these as small as possible, and that's kind of always been a trade-off. You know, how small do you make these versus how much stress do you want to put on these? Well, SAE came up with a really interesting idea. This big diode here, if you notice, is in parallel with this resistor. And in normal circumstances, the voltage drop across this is going to be so small that this is not going to come into effect. Now, a Schottky diode has a very low forward voltage drop, and it's also a very fast acting diode. So it has two good properties. So what happens is if the voltage increases across this resistor too much, the resistor has less of an influence. The Schottky diode will conduct and bypass this from becoming too big of a percentage of the load, if that makes any sense. So essentially, you get the best of both worlds. You have the emitter degeneration, but yet at high power, it's somewhat bypassed by this diode. Neat. I don't know why more people don't do that. I don't know much about this circuit, and I've not worked with it. I don't know if this is less reliable or if this, for some reason, or just too expensive, but you very rarely see this. I'm sure some of you out there who do more work with these things maybe have seen them in other amplifiers. Let me know down in the comments section if you have. But this is really cool. Another thing I've noticed is the bias circuit. Whenever you have the bias circuit, there's always a thermal tracking transistor. In other words, there'll be a transistor or a thermistor or some device like that, semiconductive device, that they'll mount onto the heatsink very close to the output transistors. And the idea is, as the transistors heat up, their properties change with temperature, because that's the way a semiconductor works. It changes its properties with temperature. And the idea is that transistor that's in the bias circuit is thermally coupled to the outputs. So as a transistor heats up, it also heats that little tiny transistor or thermistor, whatever it is, up. And then it will adjust the bias so that the bias tracks with the temperature of the transistors. Now, in this instance, they used a really innovative thing. And if you look on here, we have these two 16-pin integrated circuits, or 14-pin, 14-pin integrated circuits. And these are transistor arrays modules. So there are I believe four or five individual transistors in this, and you can use any combination or number of them that you want. But the neat thing is these have these ceramic cases on them, and they put thermal paste on these, and these are thermally coupled directly to the heatsink. So when the heatsink goes down and all the transistors plug into here underneath, the bottom of the heatsink comes in contact with this and thermally couples. Very cool. The thing I like about these is they're self-contained, so the transistors in the circuit are actually very closely thermally coupled to one another. They're very closely matched transistors, so they don't drift, and they work really well. It's kind of like having everything all in one package. Again, another thing I have rarely, if ever, seen in this type of amplifier design. So it'll be interesting to test this amp once it's all finished to actually see how all of this circuitry works. There's other innovations in this amplifier that we'll get into later after we get it working that I want to really test and see how it works. This is supposed to be a very stable amplifier, and it's supposed to even be able to take, if you short the speaker terminals, it won't hurt the amplifier. I know a lot of amps have that built in with their protect circuit, but this one's a little bit different, so it should be very interesting to see. All right, let's get our transistors put back in. All right, we're all back together now, and as you can see, I'm plugged in over here at the dim bulb tester, and what I'm going to do is I'm going to turn this on, and I just have the small 40-watt bulb on right now, and we're just going to see if this thing even powers up at all, or if the bulb gets bright, stays bright, and we have a short. I did statically check all of the connections, all of the transistors, to make sure there were no kind of short to the chassis or to any place like that. So without any further ado, well, that was bright, but it is dimming down. And if you look, the little meter as it's coming up, once you get up around 50-60 volts, it'll come up. So we have 63 volts. We're drawing 245 milliamps. And if we measure over here, the positive supply is 32.9. Of course, this is going to be 75, and negative 32.8, and there goes the phone. Okay, where were we? So we have plus and minus about 32 or 33 volts, and no shorts, and just barely, you can't see it, but the panel lamps are beginning to glow just a little bit. So now I'm going to shut this off. I'm going to turn this bigger one on, and we're going to see. Okay, now we're closer to 50 volts instead of 75. That's good. No protect relay yet. We don't have the protect relay, but that still could be because the power's too low. And now we're seeing the panel lamp starting to light up. Let's put this other one on. Ooh, did you hear that click? Protect relay just came in. And 53 volts, so just barely, but we have the protect relay. That's a really good sign. Okay, so if the protect relay came in, that means that we most likely do not have any really bad DC offset, and we don't have any bad shorts anywhere, and good possibility that the amp will work. So let's get this turned around, and my next thing I'm going to do is, right how it is set now, we're going to check for DC offset. I've repositioned the amp so we can get to things, and we're still on the dim bulb tester, and we're just going to check these two channels. Let's go to millivolts. And that's AC. Here, let's go to DC. Never mind. Okay, and we have about 48 millivolts. Yes, it's negative. Negative 48 millivolts on that channel. So there's a little bit of offset. And we have a lot more offset there. It's 120. So that might be a little bit hot, but again, with this running at reduced power, there is a possibility that some of the transistors aren't fully biased properly because they don't have their proper voltage on the circuit. So before I go to try to adjust that, I'm going to put a little bit more power. I'm going to add another bulb to the circuit right now, and that is going to raise our main voltage to 62 volts. So it's supposed to be 75, but that's pretty close. And as you can tell, the bulbs are hardly even glowing now. If you look at them over there, they're very dim, and that is simply because we have a lot of bulbs in parallel there. So now let's look, and if it gets worse, if it's still there, and yes it is. Okay, so let's start with this channel. Let's make it a little bit easier on ourselves. Hold on. Okay, I just grabbed a set of banana jumpers so that we can just plug them right in here. And let's see if we can adjust our DC offset, which is this pot that's up here. Remember, I statically set it the same as the other one. And you can see how touchy this thing is. So I can only imagine what that one-turn pot must have been like. You kind of have to wait for it to settle, I've noticed. Just giving it a little turn. Let me move the camera up so you can kind of see what I'm doing. Right here. You can see we started at negative 120 millivolts. We're down to negative 2 millivolts. So this 15-turn pot makes a big difference. How's that? I think we'll take that, huh? Okay, let's move over to the other channel and see if we can do the same with it. I have the probes on backwards. There, how's that? Okay. So we're going to do the same thing. See, when we adjust this, that really throws off the bias, you know, between the two transistors, so it has to restabilize once you move it. So it'll settle. So you just move it a little bit. And I think that's looking pretty good there. Right? Okay. Not very much adjustment was needed for that. So again, when we put full power to this thing, which we have not done, we haven't let it off the leash quite yet, but at least we know that the offset adjustment is pretty close, and I have a feeling it'll pretty much stay like this because we almost have full power up here. On the 75 volt supply, we're getting somewhere in like 62 volts, so it should be pretty close. And the nice thing is the fact that we can adjust it like that tells us that the amplifier is mostly working. So now let's check our bias. I now have the 8 ohm dummy load connected to the amplifier, and just so you know, bias is checked by measuring between the collectors of these two driver transistors, and it's really hard to hold a meter on that without slipping and shorting out on the heatsink. So what I did, just like what I did on the Lafayette on that video, I don't know if you can see it, I put a couple of, right there, a couple of little terminal strip type things that you can connect your meter to. And that's going to make it a lot easier because, again, the bias adjustment was that little green knurled potentiometer underneath the amplifier, and you reach it through the air vent slots of the bottom of the chassis, and you have to take like a flat object, like a little plastic screwdriver or something, and kind of pry the pot back and forth to adjust the bias. There's no way to adjust it with this out of the circuit like that. So it's really a hassle. So we're going to have to turn this thing up on its side if it needs adjusted. But for right now, what we're just going to do is we are going to see if, in fact, it even needs it. So I'm going to turn this thing on first of all, and we're going to let it come on. And you can see our bias right now, if the meter will stay on, is a little bit high. It's supposed to be 2.1 volts, and it's 2.28. And if we go over to the other channel, of course that's not too terrible though. If we go over to this channel and measure, this one is reading 2.28, just the same, so they're identical. I guess that's a good thing. Now, what they want done is they want it to be 2.1 volts, or you readjust it so that with a 20 kilohertz signal being fed into it at 1 watts, which would be 2.8 volt RMS output at the speaker terminals into an 8 ohm load, you should be able to adjust the bias pot to get between 0.03 and 0.04% harmonic distortion. So you need a distortion meter, and you need to measure the distortion at 20 kilohertz with the amp putting out 1 watt into the speaker load. So I think first thing we need to do is put full power to the amp to make sure that everything's going to be okay, and I'm fairly confident now it will be, because we have almost that right now. So let's switch over, and we should see, if we move down just a little bit, you should see the lights come on full brightness as well. And hopefully this isn't going to move. That goes up a wee little bit, not too much. I didn't think it was going to jump that much. Okay, this is good. So now we know that our bias is okay, or at least close to okay. Now let's look and see what our voltages look like. So here's our negative. So if we go there, well, it would help to set this right. Okay. Yeah, it is right. See if I can get a good connection. 76.8 volts. And if I go to this side, I should be positive 76.8. So everything's good so far. I don't feel anything getting hot. These drivers are just barely starting to warm up. I can feel it. Not hot, but I mean, I can feel that it's not room temperature, if that makes any sense. Okay. And I don't see the meters doing anything. So this is good. So now let's connect up a signal. Now, one of the things that the service manual mentions, and this is kind of the strangest service manual, they have amplifier repair hints, and this is really the only page you have that tells you anything about adjusting it. And it doesn't really give you a procedure, it just says that, you know, different notes for when you're checking things like the bias. There is a quiescent current adjustment on these, which is strange because normally your bias sets that, but there's a separate bias voltage and idle current, and they're independent of one another. On the later models, there's a pot for the current, idling current. On this model, which is an older one, they just shunt a resistor across the back of the board, and it's and they're looking for 20 milliamps of idle current. And if it's out, you're just supposed to experiment with different resistors until you get the right one, and then just tack it across the back of the board. I don't think it's that big of a deal. We'll see. So one of the things it says is this note. Due to the extremely wide bandwidth of the amplifier, 200 kilohertz RF fed directly into the inputs may destroy the output transistors. Well, thank goodness I don't listen to 200 kilohertz tones very often. Therefore, under no circumstances should the input cable be plugged into the amplifier while the amplifier is operating. In other words, you don't want to plug a signal in and out while this amp is turned on. You turn it off before you connect up any of your preamp or your signal generator or whatever. Under no circumstances should the amplifier be checked to ascertain if it is operating by touching the input lead with your finger. Your body acts as an efficient antenna and can transfer an excessive amount of RF to the amplifier. So let's turn this thing on its side. Well, before we do that, let's connect up a signal and just see if the amplifier will amplify. We're now hooked up to the dummy load, and I have the signal generator connected to it. You can see there. We have the distortion meter and we have our scope. And I'm just going to do the 1 kilohertz thing, and I just want to see if this thing works. So turn it on, and we'll get the scope lined up here. Okay, power on. Wow, the light's dim when that thing comes up. All right, here we go. Yay, it works. Look at that. Or, boo, it doesn't. Okay. Well, let me check some things. So after further investigation, I'm not sure what's wrong. It could be the relay contacts, which I did forget to check those, so I might check those out. It could be the level control down here has a dirty contact. I don't know. I have not cleaned that yet. Or it could be a weird thing going on with a transistor or something. I don't know. So whilst I go up to the foyer to obtain my idiot boots so that I may don them and begin the process of troubleshooting, I think I'll stop this video where it is. We'll call this part 1. We'll get it posted, and I'll have to keep you all in suspense for part 2 to see what it is that's wrong with it. All right, so on this rainy weekend day or evening, I wish you all peace, joy, happiness, and good health in your lives, and sunshine. And we'll see you all soon, and we'll hopefully figure out what's wrong with this. But the good news is at least it is passing sound, it powers up, and the protect relay comes in, which is all good news. See you soon. Bye-bye.